Ever pondered about the fate of a delicate egg dropped from the edge of space? Picture it for a moment, a speck in the vast cosmic canvas, plummeting towards our terrestrial home, fragile yet daring. The concept of an egg drop from space might seem like a whimsical thought experiment, but it actually provides a fascinating lens through which we can explore some fundamental principles of physics. For starters, let's talk gravity, the invisible force that tugs on all objects, pulling them towards the Earth's center. It's the reason you're sitting rather than hovering in your seat right now, and it would be the reason our brave egg would start its descent from the edge of space. Gravity accelerates objects, causing them to speed up as they fall. But here's the catch, it's not as simple as the higher you are, the faster you fall. Enter terminal velocity, a concept that adds a dash of complexity to our egg's adventure. As the egg falls, it collides with air molecules, creating a force we know as air resistance or drag. The faster the egg falls, the greater this resistance becomes. Eventually, the egg would reach a point where the force of gravity pulling it down is balanced out by the air resistance pushing it up. This point is what we call terminal velocity, the highest speed the egg would hit on its descent. But our egg's journey isn't all smooth sailing. At the edge of space, where the atmosphere is thin, air resistance is minimal, allowing the egg to accelerate rapidly under gravity's pull. As the egg hurtles towards denser layers of the atmosphere, air resistance increases, slowing the egg down until it reaches terminal velocity. So we've got a delicate egg, the force of gravity, and the concept of terminal velocity all playing out in a high-altitude drama. What's next for our egg? Will it arrive on Earth as a delightful breakfast surprise or a scrambled mess? Imagine the thrill, the suspense. Will it survive the fall? To truly comprehend this experiment, we must first voyage to the edge of space. Let's embark on this journey together, imagining ourselves as a humble egg destined for the heavens. Our vessel, a weather balloon, an ingeniously simple device with an impressive track record for space exploration. Its principle is as uncomplicated as it is effective. As the balloon ascends, the air around it becomes less dense, enabling it to expand and rise even higher. It's a delicate dance between the balloon's buoyancy and the thinning atmosphere. Now picture our protagonist, the egg, nestled securely within a payload attached to the balloon. It's not just any old egg, mind you. This is an egg with a mission, an egg with a sense of purpose, an egg on the edge of space. It's a brave new world for our egg, and we're here to witness its journey. As we ascend, we encounter a series of atmospheric layers, each with its unique set of conditions. The troposphere, where we humans reside, gives way to the stratosphere, where commercial jets fly. Upwards still, we reach the mesosphere, a cold and lonely place, home to meteors and rare atmospheric phenomena, but we don't stop there. We continue our ascent, pushing into the thermosphere and exosphere, the final frontiers before the black void of space. Here the conditions become harsher. The air is thin, almost non-existent, and the temperature can fluctuate wildly from biting cold to scorching heat, depending on whether we're in sunlight or shadow. Throughout this journey, our egg remains resilient, valiantly enduring these extreme conditions. It's a testament to the marvels of science and the unyielding spirit of exploration that we can even conceive of such an experiment. And so, the stage is set. Our brave egg perched on the brink of the unknown. The journey to the edge of space has been a challenging one, but it's just the beginning. Our egg has a long way to fall, a descent filled with peril and uncertainty. But for now, let's savor this moment, standing on the cusp of the great unknown. And then, the moment of truth. The egg begins its plummet. Imagine, if you will, a tiny, fragile shell, suspended in the vast, cold expanse of space, suddenly released to the forces of nature. It freefalls, hurtling towards the Earth at breakneck speed. The egg, once gently cradled in the near-zero gravity of the stratosphere, now finds itself in a drastically different situation. As our egg descends, it accelerates, gathering speed with every passing second. The forces it encounters are immense and unrelenting. The force of gravity pulls it downwards while the air resistance pushes upwards against it. This battle of forces is what we call terminal velocity. the constant maximum speed that the egg can reach in freefall. It's a wild ride, to say the least. Now let's talk numbers. At the height of 30 kilometers, our egg could reach speeds of up to 100 kilometers per hour. That's faster than a cheetah can run, the fastest land animal on Earth. But this isn't a leisurely sprint. It's a fight for survival. The egg, delicate and brittle, is subject to the brutal laws of physics. So can the egg survive this fall? Well, it's not impossible. The forces acting on the egg are, in theory, survivable. But it's the sudden stop at the end that poses the real problem. The egg, traveling at such high speeds, would need to decelerate gently to avoid cracking on impact, and that's a tall order for a small egg. As the Earth's surface grows larger and larger in the egg's path, the stakes become clear. This isn't just about an egg falling from space, it's about the delicate balance of forces, the intricate dance of physics that governs our universe. It's about survival against the odds, the resilience of life in the face of adversity. But the greatest challenge is yet to come, the final impact. The ground rushes up, the seconds count down, and then impact. The moment we've been eagerly anticipating is here. The egg, after its thrilling journey through space, meets the Earth with a jolt. This is the moment of truth that determines the fate of our brave little astronaut. So what happens? Well, there are a few possible outcomes, each more tantalizing than the other. Let's delve into the physics of the situation to understand better. First, let's think about momentum. Momentum is the product of an object's mass and velocity. As our egg hurtles through the atmosphere, it's gaining speed and therefore momentum. The more momentum it has, the harder it's going to hit the ground. But momentum isn't the only player on this stage. We must also consider the forces at work during the impact. There's the force from the egg's fall, of course, but there's also the force from the ground pushing back up. If these forces are too great, our egg won't stand a chance. It'll shatter on impact, leaving a sad, yolky mess. But don't lose hope just yet. Remember, we've seen eggs survive some pretty intense falls before. There's a chance that our egg might survive. How? Well, if the egg lands in the perfect way, it can distribute the force of the landing over a larger area, reducing the pressure on any one point. This could mean the difference between an excellent landing and a scrambled mess. Also, let's not forget the role of the egg's shape. The egg's oval shape is incredibly strong and can withstand a surprising amount of force. This could be the secret weapon that saves our egg from a crackling doom. It's a high-stakes game of physics with our egg as the main player. The question is, how does it fare? Does the egg shatter under the weight of its momentum and the forces at play? Or does it use its shape and a perfect landing to distribute the forces and survive the impact? So, does our egg meet a crackling doom? Or does it defy odds and survive? Now let's unravel the mystery. The egg's journey from the edge of space back to Earth, a thrilling plummet, has come to an end. But what does this mean for us? What can we learn from the potential outcomes of this experiment? If the egg were to survive the fall, it would be an astounding testament to the power of science and engineering. It would mean that we've developed a system capable of protecting a fragile object from the harsh conditions of space and the brutal forces of re-entry. This could have profound implications for future space travel and even for the transportation of sensitive materials here on Earth. On the other hand, if the egg were to break, it's not a failure but rather an opportunity to learn and improve. It would provide invaluable data about the forces at play during the descent and impact. It could help us refine our designs, make our systems more robust, and perhaps one day ensure that our egg, or any other fragile cargo, survives the journey unscathed. There are, of course, lingering questions about the experiment. Was the egg cooked by the extreme temperatures of re-entry? How did the parachute deployment affect the egg's descent? How much of a role did air resistance play in the egg's survival or demise? These are all important questions that merit further investigation and could lead to more exciting discoveries. In the end, this experiment is about much more than just an egg. It's about pushing the boundaries of what's possible, about learning from our successes and our failures, about the relentless pursuit of knowledge. So whether the egg breaks or bounces, its journey from space offers a thrilling exploration into the laws of physics. It's a testament to our curiosity, our ingenuity, and our desire to understand the world around us. And now, with this experiment behind us, we can't help but wonder, what other everyday objects shall we send on a space voyage next?